In this video, I'm going to walk through the rsLoRA paper, which is titled A Rank Stabilization Scaling Factor for Fine-Tuning with LoRa by Damian Kalajewski. I hope I got that pronunciation right. I'm going to start with main takeaways, then I'm going to review LoRa and the concept of intrinsic dimensionality. Then we'll dig into the rsLoRA paper, starting with definition 3.1. Then I'll go into Theorem 3.2, look at the code reference in the peft library for rsLoRA, go through their results, and I'll end with some of the ablations that they've run. So I took away 4 main points from this paper. First being the most important one, which is that the only setting of gamma r, which is the scaling factor when we multiply the LoRa adapters B and A, which results in rank stabilized adapters, is alpha over square root of r, where rank stabilized means activations and gradients do not explode or diminish as the rank increases. The LoRa paper conclusion that low ranks are sufficient is incorrect, and in the rsLoRA paper they find that for higher ranks, using rsLoRA results in lower perplexity than LoRa. I'll do a quick review of LoRa. So this is the figure 1 from the LoRa paper where they show how the adapters interact with the pre-trained weights. So we have adapter A and B. B is initialized as 0. A is initialized as a normal matrix. Both share a very small dimension r, which is the hyperparameter we set. That's the rank of our LoRa. And during the forward pass, we use both the pre-trained and the LoRa adapters, but during the backward pass, we're only updating the adapters A and B during training. So here's the forward pass during training for LoRa. We have our pre-trained weights. Let's say there's some d by d dimension. We have our scaling factor, and this is the gamma r. That's the star of the show of rsLoRa. We have a low rank adapter B matrix, which is d by r, and this is initialized as a 0 matrix. We have a low rank adapter A, which is r by d, and this is initialized as a normal matrix. And the key thing here is that during the forward pass, we need to include our pre-trained weights. And so when we think about memory savings and memory usage during LoRa, we save memory because we're not updating the gradients of the pre-trained weights. We're only updating the gradients of B and A. We also save memory because we are not storing the optimizer states. So for atom, we're not storing the momentum and variance for the pre-trained weight matrix. But we do store the weight matrix itself because we need it to calculate the activations during training. So a few high-level points from LoRa. To 1/10,000th the number of parameters are fine-tuned to achieve comparable performance to fully fine-tuned models. Only B and A weight matrices are updated during backward pass. Up to 3 times GPU memory reduction compared to full fine-tuning, which I described in the previous slide. And then this forward pass is computed during training, which includes this gamma r BA term, where gamma is the scaling factor in question for rsLoRa. I want to highlight the incorrect information, or I guess the understanding at the time that they had for LoRa. And this is from the LoRa paper. This is table 6. Table 6 shows that surprisingly, LoRa already performs competitively with a very small r. This suggests the update matrix could have a very small intrinsic rank. We argue that increasing r does not cover a more meaningful subspace, which suggests that a low rank adaptation matrix is sufficient. So this is that kind of claim to sufficiency of low ranks that the rsLoRa is disproving. And in the LoRa paper, we can see that when the rank is increased from 8 to 64, the performance stalls. And in some cases, it even gets a little worse. And so based on this conclusion, you would think, oh, okay, I guess small ranks are sufficient, and then increasing ranks doesn't get you more performance. But that was because our scaling factor was incorrect, which we'll see in the rsLoRA paper. One more concept that I want to review is intrinsic dimensionality. And I'll focus on the paper. Intrinsic dimensionality explains the effectiveness of language model fine-tuning. where they show that optimizing relatively few parameters in a low dimensional subspace, a very low dimensional subspace, of the pre-trained model's full parameter space are sufficient to achieve 90% of the full parameter performance. And they talk about this intrinsic dimension, which is the minimum number of parameters needed to reach some satisfactory solution. So, for example, 90% of the full parameter performance. And they say that an objective function's intrinsic dimensionality describes the minimum dimension needed to solve the optimization problem it defines to some precision level. And so the question is, how many parameters are actually required to closely approximate the optimization problem that is solved while fine-tuning for each end task? And so they look at 4 different models. We have 2 BERT models and 2 Roberta models. And they find that, between 100 and 1,000 parameters are sufficient to train to achieve 90% of the full parameter performance. And this is for a sentence similarity classification task. So that's some background that I think is important to understand, the importance of low intrinsic dimensionality, this idea that low ranks are sufficient. And rsLoRA is now going to challenge some of that thinking and show that we can also utilize higher ranks if we appropriately scale our LoRa adapters during the forward pass. So I'll start with rsLoRA definition 3.1. An adapter gamma R BA is rank stabilized if the following 2 conditions hold. If the inputs to the adapter are IID, such as the mth moment is in big theta R1 in each entry, then the mth moment of the outputs of the adapter is also big theta R1 in each entry. And then they say the same thing for the gradient of the loss with respect to the adapter outputs, as well as the loss gradients into the input of the adapter. So I was not familiar with big theta R notation, and I just want to break down some of the definitions, and we'll look at big theta notation in a second. So IID means independently and identically distributed. This is something we'll see very commonly as an assumption in statistics. Moments are quantitative measures related to the shape of the function's graph. So the first moment is mean, the second moment is variance, and then so on and so forth. We go to, I think kurtosis and skew and so on. And then big theta notation specifies the asymptotic upper and lower bounds of a function or algorithm. So I looked this up on Khan Academy, and they say that when we say that a particular running time is big theta n, we're saying that once n gets large enough, the running time is at least k1 times n and at most k2 times n for some constants k1 and k2. So here's n, and here's our actual running time performance, and it's bound with an upper bound of some constant times n and a lower bound of some other constant times n. So this would be big theta n, where there's like a linear relationship, so the upper and lower bounds are a function of n. So translating that to our scenario, big theta 1 would mean now we have some constant upper and lower bound. So, some k2 times 1 as the upper bound and some k1 times 1 as the lower bound. And then the actual values, can fluctuate in between those 2 bounds. So looking at this again, kind of distilling it down, we see that the first condition is that inputs are IID, which is a common assumption, and input and output moments are constant on average, and the gradient of the loss with respect to outputs and inputs are constant on average. And this is an article on Hugging Face, I think by the same author as the paper, and they say that it is proven theoretically by examining the learning trajectory of the adapters in the limit of large rank R that to not explode or diminish the magnitude of the activations and gradients through each adapter, one must set gamma R such that it's an element of big theta 1 over square root R. So going back here, input and output moments are constant, gradients with respect to the loss are constant. That's this line here, that activations and gradients do not explode and do not diminish. So what we're basically saying is that we get stable training, which means that activations and gradients do not explode or diminish. And that's what rank stable means. And the rank stable part means that this behavior, this stable behavior, is exhibited even if we increase the rank. and which we'll see in a bit. The next item that I want to focus on from rsLoRA is Theorem 3.2. And here we talk about LoRa adapters, which are of the form gamma RBA. And this is what we saw earlier in the background slides. B is D1 by R, A is R by D2, B is a zero matrix initially, and A is a normal matrix initially. That does not depend on R. And gamma goes to 0 as R goes to infinity. So there's this kind of inverse relationship. And all adapters are rank stabilized if and only if gamma R is an element of big theta R of 1 over square root of R. So in other words, gamma R has to be proportional to 1 over square root of R so that the as the rank increases, the gradients and activations do not explode or diminish. They had one disclaimer, which is that if the quality of features learned consistently depends on R, then the assumptions of the theorem may not hold. And so in practice, we require experimental validation and examination. Okay, a quick look at how this looks like in code, and it's very elegant. We have self-dot scaling for a given adapter, which is equal to LoRA alpha, so that's our alpha hyperparameter from the LoRA paper, divided by math dot square root R. So this math dot square root R is the key piece of rsLoRA. If we're not using rsLoRA, then we would have LoRA alpha divided by R. Okay, let's look at some results. The main experimental results uses the Llama 2 model. I think it uses 7 billion parameters. I didn't explicitly find it. Maybe I just didn't catch it in the paper. They used 20,000 samples of OpenORCA instruction tuning dataset, AtomW optimizer, constant learning rate. The LoRa adapters are added in all non-layer norm, linear attention, and feed-forward MLP submodules. And they use 6 different rank values for these experiments. Very small at 4 and then very large at 2048. This is kind of the biggest takeaway in terms of the results. The brown lines are the LoRa ranks and the blue lines are the rsLoRa ranks. So we see that for the brown lines, the dark brown is 4. As we increase rank, the perplexity actually gets worse, right? So we're trying to minimize perplexity, but here we're actually going in the wrong direction. So 2048 has a higher perplexity than a rank of 4. And intuitively, this doesn't make sense, right? If we have more parameters, we should be able to capture, more of the information needed, reduce our loss. For rsLoRa, we get the intuitive behavior. So we get the behavior that we would have expected, which is that for low ranks, we have this blue line, which is our perplexity there. And then as rank increases, the perplexity decreases. So at the very bottom, we have 2048, and that has, maybe, 0.1 perplexity less than our rsLoRa rank of 4. So this, in one image, we can see that rsLoRa gets us the behavior that we need, which is that as we increase the rank, we capture better performance. And then this is the proof, or evidence rather, of the rank stabilization behavior. So for regular LoRa, as we go from rank 4 up at the top to rank 2048, we see that the gradients collapse as rank increases. So this is not stable training. Whereas for rsLoRa, we see that gradients start the same, and then they stay in the same order of magnitude, whether it's a rank of 4 or a rank of 2048. So this is the pattern we're looking for when we are looking for stable training. So we'll look at some ablations, which are basically asking the question of, does this just work for Llama 2? Does this just work for AtomW? Does this just work for 1 over square root of R? Are there other variations that give us these results? So if we use vanilla stochastic gradient descent instead of AtomW, we get the same result. So LoRa, the gradients collapse. rsLoRa, the gradients are stable, and we get stable training. For different architecture, so we use GPT-J instead of Llama 2, which is I think a 6 billion parameter model, and we use GSM8K instead of OpenORCA, and we get the same results, right? So for LoRa, the perplexity doesn't improve for higher ranks. For rsLoRa, it does. And then the beige orange color are our LoRA gradients, which collapse as rank increases. And then the blue gradients are the rsLoRA gradients. They don't collapse as the rank increases. They stay within the same order of magnitude. So it's not Llama 2 or OpenOrca. Other architectures and other data sets also give us the rsLoRA results. The next question they look at is, what if we only scaled at the initialization point? So we didn't scale during training. We just scaled the initial A matrix by 1 over square root of r. That works for low ranks, right? So here's a rank of 4 down here, and that is stable. But as rank increases to 2048, our perplexity gets worse, so our training is failing. When we are training with LoRa, we get the same kind of result, the negative result, that our perplexity gets worse as our rank increases. So initialization scaling is not the solution. Another interesting question is that, is rsLoRA just a learning rate boost? So they perform a learning rate sweep between a number of learning rates, and they get a perplexity of 1.863. And the perplexity that they get with rsLoRA is 1.836. So it's not significantly better, but I think the main takeaway I took away from this is that a hyperparameter sweep, like a learning rate sweep, is a lot of training time. It uses up a lot of resources. So instead of going through that effort, yeah, you might be able to capture most of that perplexity, or I guess reduce most of that perplexity. But it's much easier just to set the rsLoRA scaling factor, and you'll get a better result. So that was my main takeaway in terms of how to practically apply this information. They also try using adapters and attention modules only, and they get the same results. rsLoRA improves as rank improves or increases, and then training stays stable for rsLoRA, whereas gradients collapse for LoRa at high ranks. They also try other scaling factors. So they try 1 over r squared, 1 over r to the 4th, 1 over r, and as well as 1 over square root of r. And they find that for these scenarios, our 1 over square root of r, which is that big theta r upper bound, lower bound constant constraint that we were looking at in definition 3.1, yields the lowest perplexity. So other scaling factors are not going to be effective. And then the last thing we'll look at is the average activations throughout training. And so this goes back to this idea that our activations should not collapse or explode during training. And they note that both for LoRa and rsLoRa, the activations are pretty stable. They're very small in magnitude when we look at the average. But the benefit of rsLoRa, if we see this green line here and this green line here, is that for high ranks, as your training goes on for longer, the activations stabilize for rsLoRa. So that was one highlight that I wanted to point out. And then when we look at the variance of our activations, we get a similar result. So high rank rsLoRa, we get this kind of plateau realization of our activations. And in general, all the activations are still pretty stable. They're still pretty small. But this kind of leveling off behavior is because of rsLoRa. All right, so I'll end with my takeaways. So again, the only setting of gamma r, which is the scaling factor of our LoRa rank adapters, that results in rank stabilized adapters is alpha over square root of r. And in general, it has to be proportional to 1 over square root of r. Rank stabilized means activations and gradients do not explode or diminish as rank increases. The LoRa paper conclusion that low ranks are sufficient is incorrect, and for higher ranks, even up to 2048, using rsLoRa results in lower perplexity than LoRa, which is what we would expect. We're training more parameters, we would expect better performance. So that's it for the rsLoRa video. A really interesting, simple, very practical research that I think is going to be really interesting to try out when I'm training my own models. So that's it, and thanks for watching, and I'll see you next time.